Hey guys, my name is Z and you're watching MakesItEasy, and welcome to IGCSE Physics edition. But today we have topic 3, which is radioactivity. And then here are the lessons for radioactivity. We have atoms and isotopes, ionizing radiation, detecting radiation, investigating ionizing radiation, nuclear equation, radioactive decay, uses and dangers of radioactivity, half-life, nuclear fission and fusion. So check out the pinned comment in the comment section for all the timestamps. So just relax and just look at what I have to say for this video. So starting with the first lesson being atoms and isotopes. So here are some definitions. Isotopes is an element that has the same amount of protons and electrons but different amount of neutrons. And atomic or the proton number is always the smaller one, and it goes by order. It's the number of protons. And atomic mass or nuclear number is always the bigger one, and it's the number of protons plus the number of neutrons. And atomic mass is also referred to atomic weight, average atomic mass, and the relative atomic mass, and MR. So the number of neutrons equals atomic mass the number of neutrons equals atomic mass minus atomic number. So here we have more atoms and isotopes. On my left here, there's some add and subtract activity for this element over here, which is carbon. So when we add an electron, the carbon 14 becomes 1 minus charge, and if we subtract an electron, the carbon 14 becomes 1 plus charge. If we add a proton, we get nitrogen N15, nitrogen 15, and if we subtract a proton, we get beryllium 13. And if we add a neutron, we get 15,6, which is an isotope. And if we subtract a neutron, we get 13,6 of carbon, which is an isotope. So here's what happens when we change, add or remove neutrons. Because the proton's number doesn't change, the element remains the same. And because the nuclear number does change, the atom becomes an isotope, because isotope is the same element that have the same amount of protons but different amount of neutrons. And here are all the isotopes for carbon. We have carbon 12, carbon 13, and carbon 14. And carbon 12 being the most abundant one, because you can see the 98.9% of carbon is carbon 12. So we move on now. Ionizing radiation for ions, particles, and isotopes. So here's for starter. What would we need to turn an atom into an ion, which is an element with charge? And the answer is energy. So here's hydrogen over here and an ion of hydrogen. It can be either this or this, depending on the charge. So here's the particles. We have protons, neutron, and electron. The relative mass for proton and neutron are the same, 1, and electron is this 2. Either this or this. Relative charge, positive, neutral, and negative. Location, nucleus, electron shells. And protons and neutrons together are known as nucleons. And for isotope, when an isotope is unstable, it emits radiation. And when an isotope has too many or too few neutrons, it becomes unstable. And atoms usually have more neutrons than protons. So you can see this diagram over here. So we'll move on now. We have alpha, beta, and gamma. And they are all types of radiation, and the symbols over here you can see. And what it's made of, alpha is 2 protons and 2 neutrons. Beta is 1 electron, and gamma is energy from the EM spectrum, and charge over here 2 plus, 1 minus, and no charge. Relative mass is 4 mu, because one proton is 1 mu and 1 neutron is 1 mu, so 4 of these is 4 mu, and beta is this in zeros. And the penetrating power, which is quite important. Alpha can be stopped by paper or a few centimeters of air. Beta can be stopped by a few millimeters of aluminium, and gamma can be stopped by very thick lead, because gamma moves very fast. And effect of magnetic field, you can have a read. And danger is inside of the body. Highest danger level, higher than gamma but lower than alpha, and lowest danger level. And we'll into Y in a second. The speed for alpha is very slow, beta is medium, and gamma is fast because it's traveled in the speed of light. Because gamma is part of the EM spectrum, the electromagnetic spectrum, which is gamma ray. and any additional information you can read. So we'll move on now. We have ionizing radiation for the motion of charged particles. So here's proton, neutron, and electron. You can see how they curve. And this only happens when the field and the particle's motion are not parallel. So in this example, you can see that proton curve less than electron. But if this were alpha particles, it will curve more because it has more charge. Because alpha particles have 2 plus charge, but electrons or beta only have 1 minus charge. So alpha particles are more heavy, so more curve. Here's a description for this diagram over here. So we'll move on now. Here's detecting radiation. So here's a recap of the property of these and the type of radiation. So for the most penetrating part, here's a fun fact. Russian spies use a rare chemical like unstable polonium to assassinate people. As the chemical is injected into the body, it emits alpha particles, which has the most ionizing energy, and doesn't penetrate all the way through the skin, which escapes the body. So we know that alpha particles are the most heavy and gamma particles are the least heavy, and it travels quite fast. So when alpha particles are injected into the body, the alpha can't escape as fast or as well as gamma radiation do, because gamma radiation can just penetrate through the skin and escape the body. Alpha particles can't, so it just stays in the body, and it's very lethal. And this is an image of a key, and the photographic film turns from white to black when it is hit with ionizing radiation, which are alpha, beta, and gamma. So we'll move on now. We have detecting radiation, which are background radiation. So from Earth, of the detecting radiation of the background radiation, we have rocks. We have from rocks, buildings, radon gas, medical sources, nuclear waste or accidents, and certain foods like coffee and banana. Because banana contains potassium, so it contains radiation, but you need to eat a lot of bananas for you to possess that harmful radiation. So don't worry about eating, let's say, banana. And we'll move on into the detecting radiation, which is the Geiger-Müller detector. So here's a basic setup. We have electrically conducting coating on the inside surface, atoms of low pressure gas over here, and thin mica window, and electrode. So here's what will happen. The ionizing radiation like alpha, beta, and gamma hits the atoms of low pressure gas, and then this in turn causes a spark caused by ionization. And then this causes a pulse of the current in the circuit. And here's a more simplified diagram. It's the same, but there's no animation. And so when this causes a current in the circuit, like a pulse, it registered as a on the surface on the screen, so we can see if there's a spark caused by ionization. So here's investigating ionizing radiation. So imagine you have 3 cookies that look identical. You have to eat one. One emits alpha, one emits beta, and one emits gamma. You're given a Geiger-Müller tube and sheets of paper, aluminum, and lead. Which cookie do you choose to eat, and how would you work out which is which? So you would most likely want to eat the one that's emitting gamma radiation and is most likely to escape your body without ionizing. And to test which cookie is which, you could use the materials provided to test the ionizing power of all 3 cookies. The one that can penetrate paper and aluminum but not lead will be the one emitting gamma radiation, as we discussed about just now in all the tables. And then we have some practicals or to investigate ionizing radiation. We use an online simulator like Isotopes uranium-238. It's blocked by these. So the reason why they registered some gamma over here is due to background radiation. So this emits alpha, and cobalt-60 emits beta and gamma, and carbon-14 emits beta. And then we have nuclear equation. For starter, uranium-238 is an unstable isotope and it undergoes alpha decay. What is the symbol, including proton and nuclear number, for uranium-238? and it's 238U and 92. What is the symbol for an alpha particle, which is 2 and 4? And predict what will happen to the nucleus of uranium-238 when it emits an alpha. It becomes thallium, which is right here. And then here's nuclear equation for alpha decay. And then for alpha decay, it's an unstable isotope emitting an alpha particle over here. So the alpha particle is a helium nucleus, as it has 2 protons and 2 neutrons. Because the alpha particle contains 4 nucleons, the nucleon number reduces by 4, which is 238 minus 4. And because the alpha particles contain 2 protons, the proton number reduces by 2. So this changes the element that the particle is. So here we have TH, thallium. After the alpha decay, it will become a radium plus A. So we have beta decay. Beta decay is an unstable isotope emitting a beta particle, 0 minus 1. And a neutron turns into a proton and an electron. And the proton stays in the nucleus, increasing the proton number by 1. And the electron is emitted as a high energy beta particle. So just like in math, the numbers of both sides of the equation must be equal. So you can see here. So you can see this diagram here. A carbon, after beta decay, it becomes nitrogen and a beta particle, or electron. So we move on to gamma radiation. Gamma radiation does not contain particles, as it is just a wave, an EM wave. This means that the proton number and nucleon number are not affected. So lastly, we have nuclear and equation. We have alpha, beta, and gamma. So you can have a read. So we'll move on now. We have radioactive decay. So here's for starter. Imagine we have 100 atoms of unstable carbon-14 and they undergo spontaneous and random beta decay. So here's some questions. What element will we have after the decay? So we know beta decay, so it will become nitrogen. And what will the proton and nucleon numbers be? We have 14 and 7. And what does spontaneous mean? It means that there's no external force acting on it. And what does random mean? It means that we cannot predict when the decay will happen. So here's more questions. You can have a read. And BQ means becquerel, and 1 becquerel means 1 nucleus decays per second. 5 becquerel means 5 nucleus decays per second. So we'll move on now. Here's more radioactive decay. As time increases, there are fewer and fewer unstable atoms. This means that the number that decay per second will decrease. And the half-life is the time taken for the radioactivity to halve, or the half-life is also the time taken for the number of radioactivity nuclei in the sample to halve. So here's a nice diagram and a graph or a simulation to show. And here's half-life. So in reality, we are dealing with much larger numbers. You can see the scale. And the first one, this one, has much shorter half-life because the scale is much shorter, it's per second, and this one is in years. And working out the half-life from a graph, and as we talked about just now, the half-life is time taken for the radioactivity to halve. And to find the half-life, first you find the whereabouts the activity axis in the initial activity has halved, and draw a line on the graph over here. Like you find the half over here, and then you just see where it meets the curve, and it goes down to the x-axis. And the half-life is around 2 years. And here's uses and dangers of radioactivity. You can have a read for yourself for how do you measure the activity of the radioactive source. And as we talked about just now, we have the Geiger-Müller counter. And then here's the difference between irradiation and contamination. So we move on now. We have what are the dangers of radioactivity. Includes mutation, cell, and tissue damage. And what are the problems arising from disposing of radioactive waste. And you can have a read. And lastly, we have described and explained the following things, how the following things work. We have medical and non-medical traces, and radiotherapy. And here are some examples for it, like the medical one here, and the non-medical one, and for radiotherapy. So we'll move on now. We have carbon dating, which is a graph of fx equals 1 over x. and there's an asymptote over here and here, so it never touches the axis. And you can read for yourself, like all living things, which are carbon-based organisms, contain a certain percentage of carbon-14. And you can never read. And uranium dating, you can never read for the uranium over here, and it decays, and decays. So move on to number 7, 8, 9. 7, we have dangers of radioactivity, which includes mutations or cells and tissue damage. Number 8, we have the problems arising from disposing of radioactive waste. And number 9, we have reduced the risk when interacting with radioactive waste. And here's some photos to go to each. We have this for number 9. This, how do we dispose of nuclear waste and the dangers of radioactivity. And we'll move on in a few seconds. And we'll move on now. We have the half-life. The definition is the half-life, as I talked about just now. It's the time taken for the radioactivity to halve, and it's also the time taken for the number of radioactive nuclei in the sample to halve. So here's an experiment to investigate the half-life, like the example. You roll your dice and never read for the process. And this R model or R experiment of how we should conduct this experiment. So move on now. We have nuclear fission. Nuclear fission is when a neutron fired at a semi-stable large nucleus, here are the key terms, to make it unstable, and this breaks down into 2 smaller daughter nuclei and 2 to 3 neutrons. And this whole process releases energy when the bonds are broken and reorganized. And daughter nuclei are when the nucleus splits and forming 2 smaller nuclei. So here are the bases of nuclear fission. A neutron is absorbed by the uranium-235 and turning into an unstable isotope, which are uranium-236. And the nucleus splits, forming 2 smaller nuclei known as daughter nuclei. Neutrons are released, and this releases a huge amount of energy. And this chain reaction happens because this neutron over here is released. That means this neutron can hit another uranium-235, and that uranium-235 becomes 236 and release a neutron, and hits another one, and this chain reaction. So here we have nuclear fission for neutron radiation. Neutron radiation is when the neutron is released during a nuclear decay or interaction, and this is known as neutron radiation. And it will have an effect on the proton and nuclear number of particles. So here's beryllium-13, beryllium-12, and neutron. And here's more on the chain reaction as I talked about just now. As you can see, the neutron, which are the green color. Whoa. Yep. So we'll move on to nuclear fission. So here's the other diagram of how it's conducted. And one thing to note is that uranium-238 is sometimes added as it won't react because uranium-238 is stable. So uranium-238 is added to slow down the reaction sometimes. So here's different numbers are correlated to different points. Then lastly, we have nuclear fusion. So fission is separating and fusion is combined. And fission doesn't require high pressure and temperature, but fusion requires, because fusion is the energy source of stars. And nuclear fusion in stars is when there's 2 isotopes of hydrogen, which are these, fused together to form a larger nucleus, helium, and a neutron. This releases a huge amount of energy as the creation of larger nuclei, resulting in the loss of mass from smaller nuclei, accompanied by the release of energy. So here's 2 isotopes of hydrogen over here, react to become helium and a neutron. So let's say if the mass goes from this over here to this after the reaction, that means that there's a loss in mass while reacting, and that loss in mass equals the energy released. And the nuclei of the product of the reaction, this one over here, has to be bigger than the nuclei of the reactant. So this helium over here, the nuclei has to be bigger than the hydrogen over here in order for the reaction to take place. And lastly, we have nuclear fission, some problems and some notes. Here are some problems with nuclear fusion. It needs high pressure to overcome electrostatic repulsions between protons and electrons. And it needs higher temperature to speed up the particle and give them condensing energy. And to maintain a nuclear fusion, the particles need to be surrounded by a perfect sphere. And some note is that nuclear fusion can happen with any two nuclei combining to form a new and larger nucleus, and as I talked about just now, the nuclei of the product of the reaction has to be bigger than the nuclei of the reactant. And energy is only released when the products have less mass than the original nuclei. And for a nuclear fusion bomb to work, it's quite a fun fact, it has to have a little nuclear fission bomb in it to supply a high temperature and pressure. I'm not saying that you have to create a bomb, but here's just a little fun fact. And here's a diagram. So that's it for this IGCSE Physics Topic 3, which is radioactivity. I hope you guys have enjoyed this, and drop a like and subscribe and comment if you have, or if you have any questions or any criticisms. And check out my Instagram in the description to support me and follow for more daily content. And I hope you guys have enjoyed my series of IGCSE Physics and more to come. And I hope you guys have enjoyed this, and I'll see you guys in the next video. Until then, stay safe and happy learning.